we are going to start the lecture on nanotechnology and chemical engineering. So today we will discuss about characterizations of the nanomaterials by using TEM. This is analysis techniques and that's basics about the same TEM instrumentations. In our earlier class we have discussed same image analysis. So here's this is also similar type of analysis techniques. So here with that few examples also we will discuss. Okay. So yeah, in this today basically basics about the SAMs we will discuss, and in comparisons of SAM and TEMs that we will discuss, and mode of operations we will discuss, sample preparations for TEM analysis that we will discuss, and few examples the image that would get that we will discuss, and acid interpretations and same image interpretations that we will discuss by considering a few examples we will consider and that we will discuss. So this is I said that nanomaterials will prepare, so that may be in the form of colloid solutions or maybe in the particles or in the form of thin films. Depending upon our applications we can prepare say different nanomaterials in different forms. Okay, that we have to analyze with the help of a specific characterization. So to get the size of that materials, crystalline types, compositions, thermal states, chemical states, optical or magnetic properties, many properties you can analyze of that particular material. So already I have discussed optical microscopes. So for that a set of lens you have to use, and then confocal microscopes we have also discussed. So with that objective lens, electrometric radiations also in additions to that you have to use to get a better image of that materials. And then electron microscopes you have discussed. So like optical or confocal microscopes, electron microscopes you have to use electrostatic magnetic lens and electrons guns that you have to use as a source of energy that would fall over the samples, and then that would energy or electrons that would be converted into the lights or that would gives a particular image with the help of instruments help. Okay. So here already we have discussed that electrons are used for this particular microscopic analysis. So TEM or SAMs whatever. So electromagnetic radiations you have to use, and electrostatic or magnetic lens you have to use instead of glass lens. Okay, so in this type of electronic microscopic we will get better resolutions of that materials or the image that surface morphology of that materials we have prepared will get better resolutions, better structural we can get. So same we can use as a analytical tools or microscopic tools for this particular nanomaterials analysis or characterizations. So TEM is also another, that is transmissions electrons microscope. So in same I said backscattered electrons is used, and thick samples no need of sample preparations. So thick sample is okay, but in case of the TEM, so whenever we prepared a material, same sample preparation is very important. So very thin samples you have to prepare the materials we get. So in case of thick samples it is okay, but here electrons beams comes and scattered electrons that would be collected, and in case it would be transmit through the samples the electrons beam. So thin samples is very important. If it is very thick, so not gives a good image of that materials. Okay. So in to actually to get or improved or better object resolution, so we have to use TEM. So here's this is very useful techniques to study nanoscale structures I said. So through this we will get TEM image, SAED selected area electron diffractions patterns will get, and particle size. These are the basic components we can analyze with the help of these instruments. Okay. So here's the basic structure of the instruments you can see. So electron source is there. So then condenser lens is there, samples or specimens is there. Through that the electrons beam is passing, and then another objective lens is there, and then here's what is transmitted electrons. So that would be collected in, and then with that we can get fluorescent skins is there. See here you can see. So with the help of that we can get a particular image with high resolutions we can get. So here this particular technique that was first developed by German scientist Max Knoll and Hans Ruska in the year 1931. After that it has been developed modified different way. So here's high resolution stems you can see. So here's the electrons beams that is multiples that is passing through these samples. See here's the samples of specimens you can see. So through that it is passing and image would get. So here basic difference are TEMs and HR TEMs. So basic In case of the TEM, so in both the cases we can get that image of that samples over which the electron beam would be focused. We can get image in both the cases, TEMs and HR TEMs, but in case of the HR TEMs, so resolution significantly much better. So here's 0.05 nanometers around that, means if samples is very small nano range, so small dimensions is very small, so let's say 0.05 nanometer I said, so that is possible. So with the help of HRTM's analysis, and it is let's say 0.2 nanometers, so then normal TEM analysis we can get, or we can see the visualizations, or whence or materials that is prepared very small range, that is 0.0 nanometers. So then we have to go for HRTM, so to get better or good resolutions of that materials whatever we have prepared. Okay, so through that we can visualize the atomic structures and lattice spacings of that materials we have prepared. Phase contrast image we can get through these HRTMs, and here's transmitted as well as scattered electrons beams, both will be useful. So I said in case of the ACM image, only backscattered electrons that would be coming from that surface of the samples that would be collected with the help of detectors, we can get ACM image. And in transmissions mode, that material electron beam that is coming, or transmitted electrons that would be collected and to get say image. These are transmitted electrons that would be fall on the specific fluorescent skins I said. So with that fluorescent skins we can get image. So here not only transmitted electrons, with that scattered electrons also, both will be collected and to get a specific image in the fluorescent skin. So that would give much more better resolutions. Okay, so in TEMS we see it's high resolutions we can get, and basic components already electron source, condenser lens, projector lens, fluorescent skins and high vacuum chamber. So these are the basic components that you have to use to get same analysis. Here basic difference in between SEM and TEMS you can see. So depth of resolutions in case of the TEMS is 1 to 10 nanometers, and lateral resolutions 0.1 to 1 nanometers normal TEMS. So HR TEMS much more better. So here magnifications is also like this we can get, and with the help of TEMS we can get 2D image, and in case of the ACMs we can get 3D image, and lateral resolutions also 1 to 2 10 nanometers. Here much more better as compared to this. So here's in case of the TEMS, thin sample preparations is required, so as if beam passes through the samples, otherwise we cannot get a good image. And applications in terms of topographical, morphological, compositions is crystalline informations we can get with the help of TEM analysis. And TEM image we get set, I said particle size, interplanar distance we can get, mapping, EDS mapping also we can do with the help of TEM analysis. And in case of same I said we can get also image with that, but here resolutions comparatively TEM it is less resolution. So here's basic means I said here is the samples, so electron beam is falling some of the samples. So these are the backscattered electrons, and this is transmitted electrons. And see here's X-ray also, means emitted X-ray that from the samples also is possible when electron gun is falling over the samples. So then these backscattered electrons that would be used for same image analysis, backscattered electrons, and this emitted X-ray whatever that is coming from the samples that would be used for EDS analysis or element analysis in case of the same. So backscattered electrons and emitted X-ray that would be collected with the help of detectors. Detector is there, here is also detector. So that only will collect the backscattered electrons, would give the image, and with the help of this emitted X-ray we will get element analysis of that materials present. And in case of the TEM, transmitted electron that would coming or falling through the samples, so it would give a normal TEM or HR TEMs. With that some scattered electrons also that would be used with that to get high resolutions TEM. So here's just electronic structures, instrument details means where the electrons guns that is falling over the samples, and it the secondary electrons or knockout electrons is coming out from that cells. The space would be empty, and then another electrons that is from the higher cells that would be come to the here means empty electrons space would be knockout electrons will be balanced by the electrons from the higher cells, and after that, so when electrons from higher cell to the lower cells it is coming, so that the energy will be coming out, that is in the form of X-ray. So that would help as a elemental analysis. I said this is X-ray, so that energy. So instruments, how it works already I have discussed. So and mode of TAM operations, many ways we can operate to visualize or to get the internal structure of the materials. So bright field imagings, so in this case only transmitted or scattered electron that would be used. Dark fields imaging, so here scattered electrons will be used to get TAM image, and HR TAMs, that is both means scattered and unscattered or transmitted electrons both would be used to get HR TAM. And with that also SAED I said that can be possible with the ACM image analysis, means these instruments. EDS analysis we can do, TAM scanning TAM also we can do. So with the electron energy loss spectra, that would help to get that. Okay, so here's a particular mode of operations you can see, and based on that the informations we can get by using a particular mode of operations, BF imaging, DF imagings or HRTM imaging, SAED. So using that particular mode of operations we can get specific informations from that materials using these techniques. Okay, so here's BF imaging transmitted mode of electrons we are using, so shape, size and morphology you can get of that materials. And DF, here's backscattered electrons, diffracted electrons we are using, crystalline regions and defects we can get with that materials whether it is having or not. HR terms both we are using, so transmitted as well as scattered electrons we are using to get the image. So here's lattice fringe, displacings, atomic structures we can get, and SAEDs with that crystal structures, phase identifications we can get, and STEM scanning. So here's in a jet contrast we can use, and with that some high resolutions mappings we can get of that materials we have prepared. And EDX analysis, we said that composition analysis or elemental analysis we can get. So here's key requirements for TAM samples. So electrons transparent through this, means the thin enough for electron to pass through that material. So I said that sample of the materials preparations is very important, so it would be thin enough so that electrons beam is passing through that materials, otherwise would not get good image. Okay, so cleans and dry, moisture free, that of course we have to use that materials. Vacuums we have to create, and special or sample preparations is very important. So some sample preparations step by steps I am going to discuss. So first steps, suppose you have a nanomaterials, and for that we have to use some solvents. Let's say any volatile solvents we can use, ethanol, isopropanol, diethyl ethers. So we can use any solvents here. So with that solvents, some nanomaterials or nanoparticles whatever we have, that we can put, make a solutions, and then ultrasonics we can through, and to break the agglomerations, ensures uniform dispersions of the nanomaterials in the solvents. So after that, drop casting methods is the step 2 step on this, and then step 2 drop casting method is there. Carbon coated copper grids for standard trim grids that is used, so we can use that, and 1 or 2 drops of that solutions whatever we have prepared in that grids we can place that, and then we can use dry airs, lamps or some heating by that way to evaporate that solvents. And also means then optional drying in vacuums also we can do to get more whatever the rest of the solvents or presence we can take out from the samples, that we can do. Okay, so here is the image of the sample grids. You can see it's very thin, so less than 100 nanometers. So copper grids that we have to use for this preparation of the samples, and very small amount of the samples will be dispersed. So in that place that samples will be placed. So very thin samples you have to prepare. Thickness is so thin that electrons can pass through that. So here's this is the step by steps whatever we have discussed. So initially that sublime surface is there, over that the nanomaterials is placed, and after that it would be transferred to the grids, and then we will sublime the materials, and then only nanomaterials will be placed in that grids. Okay, so after that it will be placed inside of that instruments, we can get that image. Okay, so many said interpretations. So said interpretations is very important for when we'll get TM analysis. With that set also will get SAD. So suppose we have a particle, so that particles may be single crystals or maybe polycrystalline materials. So if it is single crystals, one particular type of crystals is present, and if it is polycrystallines, more than one type of crystals are present, one, two or more, then may be there. So once that materials we are using for SAED analysis or TEM analysis, so there you can see different. When it is single crystals, so this type of spot type of structures would get ACD interpretations, and when it is polycrystalline, so this type of you can get. So in case of the single crystal, so this type of red spots is there. Just schematic I've drawn to get an idea about single crystal and polycrystalline materials, the nanomaterials we have prepared, and when said interpretations we are doing, so then so how it looks like. So it for singles and it's for polycrystalline, this type of ring as well as spots will be there. Okay, here silicon dioxide that was taken, same image is there. Here you can see that silicon dioxide nanomaterials that is forms. If you know that dimensions, so you can easily get dimensions is formed. So what would be the diameters or size of that silicon particles or nanoparticles is forms, and this is the ACD patterns of this particular silicon dioxide materials, nanomaterials. So here few examples I am showing. So here let's say we are preparing amorphous carbons or graphene and multilayer graphenes. Okay, so here it was prepared from nickel foil that was as a catalyst. Over there acetonitrile was used, that was heated up at 600 degrees centigrade as well as 800 degrees centigrade, both the way you can do. So once we heated up at low temperatures, then amorphous carbons or graphene that would forms, and so when it is high temperatures multilayer graphenes formations is there. So here's with the help of same image or Raman spectra also we can do. So here you can see when it was 400 degrees centigrade, 600 degrees centigrade, it was heated up these materials acetonitriles in presence of this catalyst, and graphene was formed. So here you can see D and G bands was there. Here's D band was strong here. When it was low temperature it amorphous, when it is crystalline, so here's this peak intensity gradually decrease and this intensity gradually increase at high temperature, so it is much more crystalline. Okay, so here's the TAME image, and ACAD analysis was done for that samples when it was heated up 400, 600 and then 800 and 1000 degrees centigrade. Gradually temperatures was increased when that material was prepared. So initially the image you can see it is amorphous like of structures formations is there, and then gradually that materials is agglomerated and much more crystalline structure formations is there. So you can see. Okay, so even ACD analysis also was taken, ACD patterns. So here when the materials was low temperatures it was prepared, it was amorphous and this type of spots will come, and when it is gradually increase the calcination temperatures, means formation temperature 400, 600, 800, so this type of ring formations is there, ring as well as spot formations is there. So it is polycrystallines and this is amorphous, and then high temperatures, high degree of crystallizations, multilayer graphene forms at high temperatures, this type of SAED patterns will comes, and when extremely high temperatures then single crystals of these multilayer graphenes, that's diffraction spots will get. Okay, so this is the basic changes. So when same materials if we heated up from or prepared from at low temperature to high temperatures, so amorphous to crystalline or single crystal formations is there. From this is polycrystallines, this is also polycrystallines, the graphenes that is forms, and its corresponding image also giving say good data, as well as ACED patterns also giving a good data. Here ACM image was taken for that material. So here's with the image you can find out the particle size, means specific. Here I was showing that SiO2 that was forms different particle size, here you can see. So if we know the size bar with the, here you can see iron oxide that powder was taken and ACM image was taken, and this is ACED patterns. Here nickel oxide, that was nickel iron oxide, that was heated up 800 degrees centigrade. So here in this particular powders or nanomaterials, here size was 11 nanometer. When it is heated up at high temperatures, the particle size changes, means 11 nanometer to 40 nanometers, means particle size changes, means agglomerated and larger size particles, means this is much more amorphous, this is much more crystalline. So here also ACD patterns also you can see or observe. So here's one spot, bright spot was there, and then bright spot 2, diffracted dotted spot is present. So amorphous to crystalline changes is there. At the same time, individual spots you can collect, and with that a particular size of nanomaterial that is formed, so you can categorized by counting the numbers. So here you can see this type of, this is the size of nanometer in terms of nanometer that particles form. So within that range, that percentage forms, within that range 30 percentage, this size of nanomaterials that percentage forms. So like that, so average, or you can say that a particular size of the nanomaterials that is formed for a specific method of synthesis, when that materials was prepared, the size of that nano range upwards. So you can say whether it is, means smaller diameter formations is there or larger diameters or particle size, you can easily say. Here another example is also there. So multi-wall CNT that was prepared and multi-wall carbon nanotubes. So here multi-wall CNT, here is TEM image, you can see image. So that is here. So here you can see that image that was collected. So then it was 200 nanometers the image, after that it was collected 20 nanometer, further magnifications. So similarly OLC, the onion like structure, that was, once we get these nanomaterials, carbon spherical nanometers, here you can see spherical type of materials. So when it is enlarged, it was 20 nanometers, it was 5 nanometers. So when it magnified, so then easily you can see the carbon spherical carbon nanotube, that is nanomaterials that is forms, its structure is onion like structures, that easily you can see here after it is higher magnifications. Similarly nano diamonds rod also it was taken here. Here ACM image was taken at 20 nanometers, when it is magnified into 5 nanometers. So here you can see that nanomaterial nano diamonds formations is there, surrounded with some others amorphous layers of carbon formations is there. So this is nanodiamonds and surrounded with amorphous carbons layers that is forms. Okay. So deeply we can analyze that image, whatever the materials we are prepared, and using that image we can analyze a specific materials that has been prepared, its property, structures, morphology we can get. So these applications of this is TEM analysis. So nanomaterials, its size, shapes, structures we can analyze. Catalyst also we can prepare in nano range, and that structures or morphology we can get. Semiconductors, there also we can use these particular characterizations. Metallurgy, alloy we can prepare, there also TEM image analysis we can do. Medicals research to investigate virus, bacteria, that is very nanoscales, that we can get cell structures to nanoparticle, to study the nanoparticles such as zinc oxide nanoparticles. So it's detect or identify the fracture damage in microparticles. With the help of TEM image we can do the analysis. So advantage of this TEM image analysis is, this technique is very powerful technique. So magnifications we can get very good image. So vanity applications already said, it is used to acquire vast informations, very efficient and high quality image we can get, permanent image we can get. It is easy to train use this TEM analysis. So some disadvantage is there. So this technique is very expensive, levers to maintain constant inflow of voltage to operate when we are operating. Preparations of specimens, that is very important. So once we prepared very thin samples, only then get a good image. If sample is very thick, so then we not get a good image. So these are the various about the TEM image analysis, or this is a characterization. So once we prepare nanomaterials, so we can use this particular characterizations TEM analysis to characterize the materials properties, morphology, structure, shapes, anything. Okay. So thank you. So today is up to this.